Okay, hello together. So we will go further on in statistics and in estimation, and we had some exercises left where we want to calculate some confidence intervals. And of course, I hope that you had happy and nice Eastern. I think we had really fine weather and you enjoyed some days off over the last weekend. So, ist meine Maus da? Da. No, this is the wrong one. This is this one. Here we are. We had the last time our first exercise from exercise sheet number 2, and this we find here. Okay, now we are going on with exercise number 2, and I just cut it. So a machine is cutting steel rods of a specific length out of the total production and is 150. We take a random sample of small n equals 9. Measuring their length, we obtain the length 184.2 and so on. Due to our experience, we know that the parent distribution, what is meant with the parent distribution? The parent distribution is our total production of 150, that this parent distribution is normally distributed. So before starting the calculations, from these information, what do we already know and what kind of distribution we will apply in this question? Since we do not have the information, of course, not about the total production of 150. So our sample size is n equals 9, and this means we have a small sample size. And if we have a small sample size, we are not allowed to apply which distribution? Usually we just assume, well, if we have a large sample size, then we do not have to care about the distribution because of the central limit theorem. We mostly can assume that we are approximately normally distributed. But if our sample size is small, then there was this beer guy from the Guinness Brewery in the beginning of the 19th century, and he found out that especially for small sample size, we need the t distribution. And we can only, oh, now my picture is gone. Why? So I try a restart. I think you still hear me. Oh no. Sorry for this, but I don't know. So here we are. Choosing this one. And now we are back in the game. But this is the wrong one. Then let's go here. Just a question. Did you still have seen the presentation? So for you in the internet, nothing has changed during the last 3 minutes. Okay, so then it is a hardware problem here that only the beamer is going down, but the beamer has to be still on because I can still use the second monitor in the internet. Okay, good to know. Then actually I can just go on if this happens again because you're still seeing what you should see, and then I suppose that the recording is also still working, and if no one is in the lecture hall, then I only need a virtual second monitor. Okay, so we have a small sample size, n equals 9. This means we have to apply the t-distribution, and we are only allowed to use the t-distribution if in this case we really know that our parent distribution is normally distributed. Okay, so then at first we have our random sample and we want to calculate unbiased estimators for the mean and the variance of the parent distribution. How do we do this? For the mean, what do we calculate then? We have measured 9 times the length of our steel rods. Then we just calculate what? This we have shown that the arithmetic mean is an unbiased estimator. sum xi, I from 1 to n, 1 over n. And this I hopefully have done here. So here are the data points, a bit more to the right. Just wait a minute. So these are my 9 data points, and the arithmetic mean is just summing up this and dividing by 9, 184.8. So my picture is gone again, but I don't have right now the Zoom meeting. So this is not good. Why is it still not working? Because then you cannot give me a feedback. Mm, 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 mm. So how can we solve this problem? Because I think that since I'm using my laptop, that the beamer doesn't know that I'm in here because he gets no signal, and then he moves just in the sleeping mode. And therefore I always have to restart, and this will not work. So so here it is back again. Here we are. Then I try to move the Zoom meeting to the other. Oh, only the chat is. This we leave here, and I put the chat in here, and we try it like this. Okay, so arithmetic mean 184.8. 184.8. And how do we get an unbiased estimator for the variance? Sigma hat squared equals 1 over n minus 1 sum xi minus x bar squared I1 up to n. This I have also done here, that our variance is, oops, which one did we had? 1.725. So, and B, calculate for mu a confidence interval for the confidence levels 0.9 and 0.99. Again, we think of our picture that after the standardization, xe is not 9, n is 9. xe is xi, x1 is 184.2, x2 is 182.6, and so on. Okay? So we just calculate the arithmetic mean of these 9 values. Okay. So, but now we want to calculate our confidence interval, confidence level 0.9 and confidence level 0.99. So what we need is standard normal distribution. And in the first case 9, we want that this area is 90%, and in the second case we want that this area is 99%. So what we need is to know this number here, and we need to know this number here. For a level of 90%, do I have the numbers here in my presentation? No. Then remember, where is it? No. Or we will look it up in our tables. But these numbers from, oh, sorry, we have to look it up in our, of course, in our tables, because we are in our t-distribution. So we really need our table. Where do I have the tables? Normal distribution. So plus t-distribution. Here we are. So we need an n of 9. This means oh, the chat shouldn't be in. This is not good. So first of all, I have to ask you, because I just see that if I move the window of the chat on the other monitor, this means that your names are now on the recorded file. Or you see this? So first of all, I have to ask you, is it okay that I upload this or not? Because this I don't want to do. Yep. So I move it back to the second monitor. Okay, but I move it back because this I definitely don't want in general. Okay, so back to our exercise. So we need n equals 9 and oops, where is it starting over, and 90 and 99%. So we need this table here. N equals 9, then we are at this point, and we need a confidence level of 90%. Then you have to keep in mind we want that this black area is 90% and the red area is 99%. So what is then the area of the tails? So this tail here and this tail here is then always 0.5. Oh, this should be in red. 0.5%, 0.5, 0.5%, and for 90% we have 5% and 5%. So within our table we have for 90 to look at the value with 95, and for 99 we have to look at the value for 99.5. So in one case we have 1.833, and in the other case we have 3.2498. 1.833. So this one is 1.833 and this one 2.498. This is then the red one. Oops, 3 point. 2498. 2498. So for our confidence intervals, we obtain 90% x bar plus minus. What was the formula? This is always the same. Hmm? Sigma hat over n times our value from the distribution. Sigma hat over square root of n times t 95 and n was 9. 0.95 t 0.95 and sample size n equals 9. Inserting this, we obtain 184.8 times 1.725 over square root of 9 times 1.833, and for 99% we obtain x bar, 184.8 plus minus 1.75 over 725 square root of 9 times our, then let's take this in red, 3.2498. And I think I've done this also in Excel at this case. Here we have our 1.85. Oh, sorry. Today not only the hardware is not working, also my mind is not working, because we need here within the t distribution not n, but n minus 1. Sorry. So here we need n minus 1. So also these numbers are wrong, because we have to look up the numbers for 8 and not 9. So then we go in here and we have to take this value here, 1.8596, 1.8596, and this value here, 3.3554. 3.3554. And also we have to take this 3554 and this 8596. So I think now I know how to solve the problem. I have to keep in mind that every 3-4 minutes I have to move to the second monitor, that the beamer know that we are still using the second monitor. I think this helps within our problem with the hardware. Okay, then calculating these numbers, we obtain these two numbers for our interval, that our interval is the lower limit 183.99 up to 185.61. So our interval here means 180, oops, 3.99 up to 185.61. And in this case, we have 83.33 and 27. 183.33 up to 186.27. So this is always the same procedure, that we need the number for our estimator for the mean. Then you calculate the unbiased estimator for the variance or the standard deviation, dividing this by the square root of the sample size, and then multiplying this with the value of the needed distribution. Any questions at this point? Then we move to the next question. And there we have the confidence interval for the proportion. Is it? There. Okay. And copy. Copying this and coming back to this one. So within a random sample of 144 persons in Wilhelmshaven, 75% answered they would like to shop on Sundays. Calculate a confidence interval for the proportion of inhabitants of Wilhelmshaven who would prefer a general shop opening on Sundays for a probability error of alpha is 5% or alpha is 10%. So first of all, we have Wilhelmshaven. Wilhelmshaven is a city with around 80,000 inhabitants. So this would be our parent distribution, and we have a sample size of 144. So the relative sample size 144 divided by 80,000. This is of course less than 5%. This is always, yeah, some condition we in general also have to check but this condition is mostly fulfilled. But I want that you also recapitulate this one, that we really can apply here our formulas which I presented to you in the lecture. So what are we doing then? We need our estimator. This is, in this case, a Bernoulli experiment with success 1, I want to shop on Sundays, and no success 0 if my answer is I don't want to shop on Sundays. So I need our estimator p hat for the mean. This would be then in our case the probability that I answer the question that I want to shop on Sundays. Well, just 0.75. And then we know for our standard deviation, we have our estimator, which is just the square root of pi hat times 1 minus pi hat. And then for our confidence intervals, sample size is larger than 30. This means normal distribution. Standard normal distribution. Oh, I have to change this here. This is not the normal distribution, but this has to be the t distribution. So in this case, we go in here and again, this one should be 95%. So these two are 2.5%. So we need our value from the normal distribution, which is associated with 97.5%. This value we had quite often, but again, let's look it up in our table. Normal distribution is here. %, and then we are here 97.5, and then we are here again 1.96. So what we then need is our interval is given pi hat plus minus sigma hat over n. So square root of 0.75 times minus 0.75 over 144 times 1.96. This is for a confidence level of alpha is 5% and for a confidence level of alpha equals 1%, we obtain p hat, again plus minus 0.75, 1 minus 0.75 over 144. And now we need the numbers where we have this area is 99%, so the tails are both 0.5%. So we need the number with 99.5, and then we are almost at this point, so 2.58. So this number is then 2.58. This number was 1.96. 2.58. And this I always did for you within Excel. So here I have my n is 144, pi hat is 0.75, sigma hat is just square root of 0.75 times 1 minus 0.75. For an Bernoulli experiment, this is just equivalent to the arithmetic mean. And then we have to divide this by square root of the number of the sample size. So divided by square root of 144. Confidence level is 0.95. And of course, then since we have a two-sided interval, we need the value of the normal distribution for 97.5%, and this we obtain by the inverse normal distribution using our interval here, confidence level of 95%. And then, we obtain, of course, also within Excel 1.96. And then we have the interval borders limits of 0.68, 0.82. And this means then 0.68 up to 0.82. And here we only change the confidence level 95%. Oh, sorry, it is not 99, but 90. Sorry. So I didn't read my own exercise. So here we need 90. Oops. 90%. And if we have 90%, then every tail is 5%. And if every tail is 5%, again here, then we need 0.95, and then we are roughly at 1.6. 0.95, 0.64, this one. This is the closest value to 0.95, 1.64, and then this one is 1.64, and this also. And then our limits, if we put this in, is 0.69 and 0.81. 0.69 and 0.81. Okay. And the last question. Calculate the confidence level if the confidence interval would be represented by 75% plus minus 10%. So now we are coming from the other side. Now we know our confidence interval and we want to calculate which confidence level represents a given interval. But our interval is given by 0.75 plus minus 0.1. So our interval is given by 0.65 up to 0.85. The question is confidence level. So in general, we have p hat plus minus square root of p hat 1 minus p hat over n times z. This represents, in general, our confidence interval. Now we know the limits of our confidence interval, 0.65 and 0.85. Then how we obtain our confidence level. Graphically, what we now know right now is that, oops, we're coming, so to speak, from our distribution here, 0.75, 0.65, 0.85, and what we want to know is the area here. And we know that we can transform these two numbers, 0.65 and 0.85, into a standard normal distribution. But in this case, Z down and Z up, these two numbers we don't know. This we have to calculate. But if you look at this here, then 0.75 is this, and 0.1 equals this. So from this we know square root of p hat times 1 minus p hat over n times z equals 0.1, or if we inserting our numbers, 0.75 times 1 minus 0.75 square root over 144 times z equals 0.1. Let's take this to the next slide. Oops. Up. Square root of 0.75, 1 minus 0.75 over 144 times z equals 0.1. And then we obtain that equals 0.1 over 0.75 times 1 minus 0.75 over 144. Did I calculate this in Excel? Hopefully. Oh, better. This one, confidence level 0.65. And then we obtain a Z value of 2.77. This is true. This sigma hat. Yeah. 2.77. Well, and with this value, 2.77, we can go back in our table, and now we look at the value corresponding to 2.77 is 2.77 here. So we are here, and this corresponds to 99.72%. To 99.72%. But now you have to keep in mind, again, we have a two-sided confidence interval. That this then mean, as we have done it in the two other cases, here this was the Z value corresponding to 97.5%. So in the end, in order to calculate the alpha error, we then need that we have 1 minus 99.72% equals to 0.28%, and this we have to multiply by 2 in order to get the alpha error, because we have a two-sided confidence interval. So alpha equals 0. Oh, not percent here. 0.56%. Okay. We will also do some further exercises on this, because I think you really have to practice it, and maybe you have done over Eastern something else and not looking into statistics books. This is also okay. Okay, but since we have lost today much time because of my hardware problems here, we will do the last exercise the next time. Maybe you can look in and do it as a homework, and we will do today some content of the lecture in the last 15 minutes. So let me go here, because what we also of course, want to do is hypothesis testing. And this is maybe, yeah, the things if you making some marketing analysis and asking people downtown if they want to buy some products or anything else, then you are interested, is your hypothesis you have made that they like this product or not, is it true given a specific confidence level or not? And this is, of course, highly correlated to the calculation of our confidence intervals, but we want to start with this. So if we assume that we have a random sample and we want to test some hypothesis about this sample, and especially we make some hypotheses about the parameters of the distributions. So we make a hypothesis that the mean of our distribution is larger than a specific number or something like this. And since we are doing statistics, of course, we have at the beginning to say to what specific level, to what specific probability error we are considering that the probability that we have a probability that we are making some wrong decisions. Then, of course, still we do not know the parent distribution. And therefore, this specific probability error is then the probability that our hypothesis would be not confirmed, or that our hypothesis is actually not true for a given probability error. And this, of course, you always have to do in advance, because sometimes people start to pick some random sample, then analyzing this, and then they look at the numbers and they find, okay, I would not reject my hypothesis up to a level of 2.5%. But this is then the wrong way, because at first you have to think about the right size of your probability error. Because otherwise, yeah, so to speak, you would take the right probability error that you obtain the result you want. And this is not what statistics is about. So, but let's take some example to make it more practicably. So in your company, you want to know if your marketing activity has increased the awareness of a product. You know that in general, before you have made your marketing activity, that the awareness of your product was roughly 40%. So 40% of your parent distribution have known your product before you have started your marketing activity. Now, after your marketing activity, it would be too costly to ask everybody here in Wilhelmshaven or everybody in Niedersachsen. So, and therefore, of course, we make some survey. And within this survey, we ask 1,000 people. Remember, on Sunday, we have the polls in France, our neighbor. And then also, in advance of the poll, we just asked the people how many people would vote for Marine Le Pen and how many people would vote for Macron. So something similar we are doing here. We have made our marketing activity, and now we are asking 1,000 people. And within this 1,000 people, 420 people answered that they know our product. Then, of course, 420 over 1,000 is 42%. If we are doing only descriptive statistics, then you would just say 42% is larger than 40. Okay, more people are knowing my product. And this would be then the end. Hurrah! I made a good investment decision because now my marketing activity was a success, because now 42% of the people are knowing my product. Well, if I only use these informations for my market activities, then I don't think that this is really a good choice. Because here we asked specific 1,000 people. We could also go downtown and ask another 1,000 people, and maybe in this sample of other 1,000 people, maybe only 390 people answered that they know your product. So from this, we cannot answer the question, has the awareness of the product increased within the total population? Why? Because these are specific people, and other 1,000 people can answer in another way. And in general, we will have in our random sample statistic random fluctuations. So only a point estimation is, of course, not enough in order to decide that our marketing activity was really a success. And now the hypothesis testing comes in. What is hypothesis testing asking? We ask, is it possible to reject our null hypothesis? And what is the null hypothesis? The null hypothesis is just that we say the awareness of our product has not changed. Quite often we take as one hypothesis, nothing has changed. And now we take our random sample with 1,000 people and we ask, is it possible to deny this hypothesis that nothing has changed because 420 people out of 1,000 have answered with yes, and this is obviously larger than 40%. But due to these random fluctuations, we cannot directly answer this question, but we have to specify some probability error, for example, 5%. So for a confidence level of 95%, we just ask, is it possible to reject our hypothesis that nothing has changed with a probability of 95%. And this we always have to connect our question and our confidence level or our alpha error. So how would we then create such a testing? So the first question is, of course, we formulate two hypotheses. And one hypothesis is quite often nothing has changed. Or in general, we say that our hypothesis is that our parameter equals some specific number. And the alternative hypothesis would be then our parameter is not equal this number. And then, of course, we can move to the right side and we can move to the left side. And this means that we are then making a two-sided test. This corresponds to a two-sided confidence interval. Or we assume that our parameter is equal or larger than a specific value. Then the alternative hypothesis is our parameter is smaller than our specific value. And this, of course, is then a left-sided test, and the other way around. If we assume our null hypothesis is our parameter is equal or smaller than some specific value, then the alternative hypothesis would be our parameter is larger than a specific value. And this, of course, is because we are moving to the right, is called a right-sided test. But then, and this is, really important, because mostly in statistic courses, sometimes we don't talk about this. Then we, can more or less talk about two kinds of errors. And in general, we will use only these alpha errors. Because if we then calculate from our random sample, is our parameter larger or smaller than some specific value, what can happen? It can happen that from our random sample, these 1,000 people we ask, this is only this is only a sample, and these are not the whole population of, let's say, Wilhelmshaven. Then it can be possible that from the information we took out of our random sample, we reject our null hypothesis, but our null hypothesis is still true. So in our example, it could be possible that we have just asked, so to speak, the right people, which by random just moved on our web page, and they saw, okay, here is some new web design, and therefore they found your product. And by accident, you just ask many people within this 1,000 people who just clicked on your website. But in general, not really more people have clicked on your website. And Wilhelmshaven has 80,000 inhabitants. So it could be still possible that if you taking, let's say, 10, 15 other samples, random samples of size 1000, that always we do not obtain an result that more than 40% know our product. And this is called the alpha error. From our experiment, giving, let's say, 95% confidence level, we reject our null hypothesis. Yes, of course, my marketing activity was a success. I can assume up to a level of 95% that more people are knowing my product. But it can be possible that in general, not more people know my product. But then we can also take this the other way around. And this is then called the error of the second kind, or beta error. And this means it could also be possible that from my random sample, I'm not rejecting the null hypothesis, although it is not true. Because now I just asked by random some people who, wasn't looking around, but in general, most of the people have clicked on your new web page, so to speak. But in general, we will use also in this statistic course these error of first kind, the alpha error, and this then would mean we want to be quite sure that we are right, and therefore, of course, in general, we would choose this alpha error in quotation marks to be quite small. But I really have told you in advance, you really have to choose the right alpha. And this right alpha level, this of course depends on the setup of your experiment. And what we then just calculate is a conditioned probability. The probability not to reject our null hypothesis given that the null hypothesis is true equals our alpha error. And just choose a small alpha error, then we have the following probably. If we just say, let's take 1% or 0.1% always as our alpha error, that if this alpha is small, then this would mean not rejecting the null hypothesis is of course increasing then, and this we will see, then our confidence intervals becomes broader and broader and broader. And with this we will end today. This of course, if we say then 99% and this maybe 90%, if we move it out, then we have here maybe 99%, and then the interval for not rejecting our null hypothesis becomes larger and larger and larger. And therefore, it is really important that we choose the right alpha, but also in practice, we mostly use 1, 5, or 10%. And this is quite often, and in my understanding, it is right to ask if these general levels we always choose, if these levels are really the right levels. Okay, then next time we will do the last exercise, and we go further with hypothesis testing, and we will also, of course, start to calculate practical examples with hypothesis testing. Oops, no, it